Truly foundational, really the very fabric of how we understand our world through mathematics. We're going to investigate a really provocative idea. What if our entire mathematical system, wasn't built on the familiar sort of rigid structure of the square, but on the perfect form of the sphere? You've shared some incredible sources that honestly make you question these foundational assumptions, and our mission today is basically to uncover the most surprising, the most important insights from them. We'll explore the bedrock of our current mathematical system, imagine what a sphere-based system would actually look like, consider how it might change the way we visualize data, and maybe most intriguingly, what it would do to that famous constant.
Yeah, and what's really fascinating here is that this isn't just some, modern thought experiment. This inquiry taps into a really ancient philosophical tension. It actually stretches all the way back to the classical problem of squaring the circle. That was, for centuries, this quest to reconcile these two opposing concepts, the circle and the square. And while the idea of sphere-based math might sound kind of intuitive at first glance, this journey, well, it's going to lead us directly into some revolutionary concepts. Things like non-Euclidean geometry. These are mathematical systems where some of Euclid's sort of obvious rules just don't apply. And it highlights a really critical difference from, say, René Descartes' work.
That's a great setup. So, okay, to really appreciate what a sphere-based system might offer, maybe we first need to understand the square world we currently live in, mathematically speaking. It's a world built on axioms, right?
Exactly. The ancient Greeks, especially with Euclid's elements around 300 B.C.E., they formalized geometry, turned it into this rigorous deductive science. Euclid laid out this framework based on fundamental definitions and, crucially, postulates. A lot of these postulates are so intuitive, they almost feel like universal truths.
Yeah, things like, being able to draw a straight line between any 2 points, or extending a line indefinitely.
Right. Or drawing a circle with any center and radius, or the idea that all right angles are congruent, they're equal to each other, they just seem self-evident.
They really do. But then comes the point where things get, well, really interesting. The fork in the geometric road, as it's often called. Euclid's fifth postulate, the parallel postulate.
Precisely. It states that for any given line and a point not on that line, there is exactly one line through the point that doesn't intersect the given line, basically one parallel line. Now, for centuries, mathematicians tried to prove this postulate just using the other four, and they failed. But this failure, maybe surprisingly, led to this profound realization that other perfectly consistent geometries could exist just by changing this one axiom. It's like discovering that if you just tweak one rule in a game, you create an entirely new, equally valid game.
Wow. Okay, and then let's fast forward to the 17th century. René Descartes comes along, and he gives us the Cartesian revolution. This is really the root of our square-based mathematics, isn't it? You know the legend, right? Descartes is lying in bed watching a fly on the ceiling.
Yeah, the fly story.
And he realizes he can pinpoint its exact location just by measuring its distance from two perpendicular walls. And boom, the Cartesian coordinate system is born.
It's a fantastic story, whether it's entirely true or not. But that system, with its XY coordinates as perpendicular axes, it's a direct and incredibly powerful application of Euclidean axioms. That grid it forms, it inherently assumes the parallel postulate holds true. The genius of Descartes was bridging algebra and geometry, describing a circle with an equation like x squared plus y squared equals r squared. So the primacy of the square in this system, it isn't just about looks, it's not aesthetics. It's really about the simplicity, the linearity, the orthogonality, those right angles that lets algebra be so elegantly applied to geometric problems. It unified two huge branches of math.
Okay, so if our current system is so fundamentally square, tied to these Euclidean rules and Cartesian grids, what does that mean for our idea of a sphere-based mathematics? I mean, does such a system even exist in a formal way?
Oh, absolutely it does. It's called spherical geometry. And it's simply the geometry of the two-dimensional surface of a sphere. That's the playing field. In this world, points are just locations on that surface, pretty straightforward. But what we call lines are actually geodesics. These are the shortest paths between 2 points on the curved surface. Think of them as arcs of great circles, like the Earth's equator, or lines of longitude running pole to pole. Those are the straight lines on a sphere.
That makes sense, visually anyway. But what's the most, striking difference? The thing that really separates it from our everyday flat Euclidean geometry?
I'd say the most mind-bending departure, the one that really breaks from Euclid, is that in spherical geometry, there are no parallel lines. None at all.
Right, none.
Zero. All great circles, all these spherical lines must intersect each other. In fact, they always intersect at 2 points that are diametrically opposite each other, like the north and south poles for lines of longitude. This directly violates Euclid's fifth postulate, the parallel postulate. It really forces you to rethink what straight even means when you're not on a flat plane.
That's a complete paradigm shift. So how does that mess with something as basic as a triangle then? What happens to triangles on a sphere?
The properties of triangles on a sphere are just fascinating.
Mm-hmm.
First off, the sum of the interior angles of any spherical triangle is always greater than 180 degrees.
Always greater, not equal.
Always greater. We actually call that extra amount the spherical excess. And get this, the triangle's area is directly proportional to that excess. So triangles with bigger angles literally take up more space on the sphere.
Whoa.
And here's maybe the wildest part. In spherical geometry, similarity implies congruence. All similar triangles are congruent, meaning if two triangles have the exact same 3 angles, they must also have the exact same size. They're identical. You just can't have a small triangle and a large triangle with the same angles, which is totally possible, even common, in flat Euclidean space.
That is genuinely hard to wrap your head around. Okay, so another fundamental difference then seems to be that spherical geometry is finite, right? Even though it's unbounded, you can keep going. Any line is a closed loop of a finite length.
Exactly. A great circle has a finite circumference.
And this would completely reshape concepts that rely on infinity, wouldn't it? Concepts which are so core to our current Euclidean system. So, okay, with these sort of spherical principles in mind, it makes you wonder, how would something as common as, say, a bar graph look if it truly embraced a curved space? Can we really visualize data effectively on a curve? Let's talk about this idea of a spherical bar graph.
Right. Well, maybe first, let's just quickly think about why the standard bar chart is so effective. Why does it work so well?
Well, they all start from the same line, the baseline. So you just compare heights.
Exactly. That common baseline makes it incredibly easy for our eyes, for our brains, to compare lengths and therefore magnitudes accurately. It's simple, it's linear, it's really effective for those straightforward comparisons.
Okay. But the idea of curved axes or visualizing things spherically isn't totally, out there. We do have some real-world analogs, don't we?
We do.
Like the polar area chart, the one Florence Nightingale famously used back in the 1850s.
Yes, the Nightingale rose, a classic example.
Right. It divides a circle into sectors, wedges like a pie chart, but the value isn't shown by the angle. It's represented by the area of that sector. And that area changes because the radius varies. It's fantastic for showing cyclical data like monthly death rates in her case.
Absolutely. But crucially, it comes with a known perceptual pitfall. Because area scales with the square of the radius, remember A equals pi r squared, roughly even small differences in the actual value can look much bigger visually. It can exaggerate differences, making precise comparisons harder than with a simple bar chart where length is linear. So it trades some precision for showing patterns over time, especially cycles.
Okay, that makes sense. And another analog that comes to mind is the radar chart, sometimes called a spider chart.
Yep, another good one.
Its purpose seems a bit different, though. It's less about comparing single magnitudes and more about comparing overall profiles of multiple items across several different variables.
Yeah.
Like comparing different products based on price, features, reliability, that sort of thing.
Exactly. You're looking at the overall shape that the connected points make rather than just the length of one spoke. If we take the term spherical bar graph more literally, actual 3D spherical bar graphs do exist. You see them in specialized software, things like MATLAB. They're used for geospatial data visualization. Imagine mapping population density or maybe resource distribution across the Earth's surface with bars literally sticking out from the globe. So the concept is definitely used in specific fields.
Right. So it seems like these analogs, they validate the intuition behind spherical visualization, but they also highlight a really crucial principle. The squareness or linearity of the traditional bar chart is what optimizes it for simple, accurate magnitude comparison. These spherical or circular alternatives seem to be more specialized tools, maybe not universal replacements. They often trade that kind of direct clarity for other goals, like showing cycles or holistic profiles or geospatial relationships.
That's a very good summary. It's about choosing the right tool for the job.
Okay, now for what might be the most intriguing question that pops up with this whole sphere-based math idea. Does shifting to a spherical framework somehow solve the infinite, messy nature of the seek? Could it perhaps simplify pi down to a nice, neat whole number, as some people seem to hope?
Right. This is a really common point of confusion. And the answer is emphatically no. It does not.
Okay.
This idea rests on a pretty profound misunderstanding of what actually is. You see, pi, the number roughly 3.14159 and so on, is rigorously defined as the ratio of a circle's circumference to its diameter, specifically within the framework of Euclidean geometry, flat geometry. Its value is a logical consequence of those Euclidean axioms we talked about earlier. It's baked into the system. It's really a fundamental constant of the real number system itself, not just some property of a physical circle you might happen to draw.
So it's not just an accident of measurement. It's defined within that flat Euclidean space. And it's also famously an irrational number, right? It goes on forever without repeating.
Exactly. It's irrational. And even more profoundly, it's a transcendental number.
Transcendental, meaning.
Meaning it fundamentally cannot be the solution, the root, of any polynomial equation with integer coefficients. Like, you can solve x squared minus 2 equals 0. The answer is the square root of 2, which is irrational but algebraic. Pi isn't like that. It transcends algebra, in a sense. And that quality, its transcendence, is the definitive mathematical reason why the ancient problem of squaring the circle, constructing a square with the exact same area as a given circle using only a compass and straight edge, is impossible. You simply cannot construct a length equal to the square root of pi using just those tools.
That makes perfect sense. It's not just hard, it's provably impossible because of the nature of pi itself. Okay, so if pi is defined in Euclidean space, what does happen if we go back to our sphere and try to measure a circle on its surface? Like, draw a circle around the North Pole, measure its circumference along the curve, and divide by its diameter measured through the sphere. Let's call that ratio, pi prime.
Right. So you perform that measurement on the sphere. What's fascinating is that this measured ratio, your pi prime, is not the constant. It's different. On a sphere, this measured pi prime is always less than. Always. And what's more, it varies depending on how big the circle is.
It changes. It's not constant.
It's not constant on the sphere. For a very, very small circle on the sphere's surface, the measured ratio pi prime will be incredibly close to the Euclidean. That's why a small patch of the Earth looks flat to us, and Euclidean geometry works so well locally. But as the circle gets bigger, the measured ratio pi prime gets smaller and smaller than mole. And for the largest possible circle, you can draw on a sphere which is actually a great circle, like the equator. The circumference is 2r, but the diameter measured straight through the sphere is 2r. So the ratio CD approaches. Well, it is if measured along the surface in a certain way, but if you think of the diameter as the straight line distance through the sphere, the path along the surface is longer. Sorry, let me rephrase. If you measure the diameter along the curved surface from one point on the circle through the center to the opposite point, that distance is actually kerr for a great circle. The circumference is 2r. The ratio is 2bar, which is 2.
It approaches 2 for the biggest circle. Wow.
For a great circle, yeah, the ratio of circumference to the curved diameter path is 2, so deviates significantly from...
Okay, so the crucial point here is we're kind of mixing up two different things, aren't we? It's a category error. We're confusing a mathematical definition, the constant pi, which is defined and has its value in flat Euclidean space, with a physical measurement, the ratio CD, which we are measuring on a different curved, non-Euclidean surface. They just aren't the same concept.
Precisely. That's exactly it. Changing the geometry you're working in doesn't magically change the definition of the constant Po. It just reveals that the specific property that the ratio CD equals is a special characteristic of Euclidean space. It's not universal across all geometries. In fact, the amount by which this measured ratio deviates from Po is actually a way to quantify the curvature of the space itself. Positive curvature, like a sphere, gives a ratio less than pi. And just to complete the picture, there's another type of non-Euclidean geometry called hyperbolic geometry, which has negative curvature, like a saddle shape. In that space, the measured ratio of a circle's circumference to its diameter is always greater than s.
Fascinating. So acts like a benchmark for flatness. Okay, so pulling this all together, what does this mean for us?
We've seen that, mathematics based on spheres is not only possible, it's well understood. It's spherical geometry. And the idea of a spherical bar graph also has these powerful real-world analogs, although they seem to come with definite trade-offs in terms of that direct, simple comparison we get from standard charts.
Yeah. And perhaps most importantly, we learn that the core premise that sometimes comes up, that switching to a sphere-based system would somehow simplify or change its fundamental nature, is just incorrect. It misunderstands what pi is. Adopting spherical geometry doesn't alter the definition of BAF. It simply reveals that the famous ratio of a circle's circumference to its diameter is only equal to in a flat Euclidean space.
So if we kind of zoom out and connect this to the bigger picture, this whole inquiry into spheres versus squares It really leads to a deeper appreciation of mathematics itself, doesn't it? It really shows how our mathematical systems are consequences of foundational choices. Those axioms we start with really matter. They absolutely do. And modern mathematics actually has ways to unify these different geometric worlds. We use the concept of a manifold, which is an abstract space that if you zoom in really close on any small patch, it locally resembles flat Euclidean space. Think about the Earth again. Globally, it's a sphere, obviously curved, but your immediate neighborhood looks pretty flat, right? Manifolds capture that idea mathematically, allowing us to use calculus and other tools even on curved spaces.
Okay, and this brings up maybe a really important point for you, the listener, to consider. The discovery of these non-Euclidean geometries, which, remember, stemmed from questioning just one seemingly obvious axiom, the parallel postulate, it proved something profound. It proved that mathematics isn't just a single monolithic description of reality.
Exactly. Instead, it's this rich collection of diverse, internally consistent logical systems. We actually have the freedom to choose our foundational axioms, and that choice determines the rules of the logical universe we decide to inhabit and explore. The Euclidean system is so dominant in everyday life and much of science because it's extraordinarily useful and accurate for describing our local everyday world. It works. But the spherical system is a different tool, perfectly valid and better suited for other tasks, like global navigation, or mapping the cosmos, or understanding the geometry of space-time in general relativity.
So think about how this might apply beyond mathematics. Where else in your life, or maybe in your work or your thinking, might a single, unchallenged assumption, something that seems as obvious as parallel lines, be shaping your entire perception of a problem or a situation, or even another person? What might happen if you consciously questioned that assumption and explored the alternatives? That's definitely something to mull over. Thanks for joining us for this deep dive.